Okay, then hello everyone online and here in the room. Today I will present about one of our projects, the REuse project. I'm a researcher at the Center of Expertise Water Technology, or CEW. And my background is I studied chemistry, and later I did a PhD more in enzymology, biochemistry. And for a couple of years, I worked as researcher in the University of Groningen and produced bioplastic with bacteria. From CW, I also work as a water technologist for 2 days a week at the local water authority, Wetlands. But today I will talk about this REuse project, and it stands for the reuse of GArmerwolde municipal effluent for industrial processes. So the aim is to produce industrial process water out of effluent from a municipal wastewater treatment plant. Here are our partners in the project. It's together with Water Laboratory North of the Netherlands, WLN, Local Water Authority Noorderzeilvest, North Water and us, and sponsors are Waterfonds, Nationaal Programma Groningen and Ames Delta Green. I will give a short outline of the presentation. It has 2 parts. In the first part, I will give an introduction on REuse, like what is water scarcity in the Netherlands? Is there water scarcity? Is there water pollution? And something about industry water. And then we might have a small break, depending how fast it goes. Or you can ask questions in between. And then at the end, the second part, I will tell about REuse pilots. We are testing 3 pilots in this project. Capillary nanofiltration, BODAC, and Wetlands. So this project REuse, well, I already told it stands for the reuse of GArmerwolde municipal effluent for industrial processes. This whole project runs from 2022 to 2025. And within REuse, we are testing on a small scale 3 different pilots to see if we can produce industrial process water, but on the other hand also remove medicine residues left in the water. So then why are we doing this? What are the water chain challenges in the province of Groningen? Well, the fresh water availability in the Netherlands is, well, there's a lot of water, but the amount of proper fresh water is limiting. And besides that, the population and the industry of the Netherlands is still growing, and also the industry needs more and more fresh water. And besides that, people use medicine, so also the amount of micropollutants in the water is present and also increasing. Here is a small overview of what happens in the province of Groningen. So water is coming in from some rivers and going out to the sea in multiple places. And during dry years, you might get some issues with water, and also this province has some issues with salt water coming in from the sea. So you cannot pump fresh water all over the province, only in the south, because in the north it's more salty from the sea. This is an overview of Vewin. They made a graph of, they asked all the water drinking companies in the Netherlands, there are 11, like how is the situation at the moment and does it need action? And all the red ones, they said they need action. So in the near future, the amount of drinking water might be limited. And on the other hand, you see the yellow dots. That means that there are some housing construction plans. And in some places, the bigger dots, the plans are to build 25,000 houses or more. So that might be an issue if that is in a region where the amount of proper drinking water is limiting. So we need to look for solutions. Then back to the province of Groningen. I thought that the amount of the number of people is growing in the Netherlands, but also the industry is growing, especially here in the north, around Eemshaven and Delfzijl. So the Eemshaven likes to extend with data centers, electricity centers, and the production of hydrogen with a full-scale factory. And they estimate that they need between 2030 to 2035 and beyond, approximately 25 million cubic meters of water every year, which is a really large amount. And the Delfzijl industrial area needs an addition of 5 million cubic meters per year, which means that in total, this whole area in the north, where, well, the amount of fresh water is limited because it's close to the sea, so you cannot pump it there, needs 30 million cubic meters per year. And then here's a picture to compare it. The drinking water company in this province of Groningen, at the moment they produce 48 million cubic meters per year. So that means that it's almost doubling if the industries that need that much water. Another issue that we need to deal with is the amount of pharmaceuticals in the water. People, of course, some people take medicine and then it's metabolized in their body, and then both the metabolites and sometimes the medicine as its own go to the sewage and then to a sewage treatment plant and then to surface water. And here's a nice graph made in 2016 about the amount of pharmaceuticals found in the environment. So it's found in all places, like surface water, tap water, groundwater, and other drinking sources. And you can see that, and it's not the amount in total of medicine, but the number of different medicines. So in the red countries, they found more than 13, in some cases more than 100 different types of medicine in the different sources of water. Then back to the north of the Netherlands. This is a picture of diclofenac, a painkiller. And you can see here that it's distributed all over the Wadden Sea, which is a UNESCO heritage site. So it's a nature reserve, so it would be better if there are no medicine, but clearly it's present. And the Payneck value of the diclofenac is 0.05, and I think, well, it's a bit difficult to see because it's all red, but it might be that the Eems estuary is already over that value. Well, it's estimated that approximately 1.5 billion Dutch citizens in the north of the Netherlands discard approximately 21 tons of medicine residue every year. Or if you calculate it back to per day, it's 57 kilos per day to the Wadden Sea. And only to this Eems estuary, it's 45 kilos per day. So a really large amount. And I think the majority is coming from the sewage treatment plant. So if we can remove the medicines there, it would be a great solution for this whole nature reserve. But also the Dutch Institute, KRW, has guidelines that requires more clear drinking water in the future. So REgain is also piloting this approach, not just to produce drinking water, but also look like how can we make the water more clean and remove all the medicine pollution. Well, to get to the 30 million cubic meters per year, there's this is the big picture, how the province of Groningen likes to accomplish that. In the first step, they make a water factory, and they do it here close to the capital city of the province, Groningen, here in GArmerwolde. They take water from the Eems channel purify it to process water, and then pump it via a big long pipe to the industry in the northeast of the province. But it's not an exhaustible source. The Ames channel is not that big that you could take all the 30 million cubic meters out of it. The second step is to produce another 10 million cubic meters from wastewater effluent. And the last step is to recycle another 10 million cubic meters of water in the industrial sites. Then phase by phase. Here's the first part to produce the first 10 cubic meters, 10 million cubic meters. This is done by the company Northwater. And they produce industrial process water out of the Ames channel. It's operating since 2021. And the first customer was a big data center for cooling water. And as I already said, the Ames channel is not an inexhaustible source, so you cannot produce all 30 million cubic meters from it. The second phase is the REgain project, where we are part of. And the idea is to make a full-scale water production plant, which removes also medicine from the wastewater. So it takes in effluent from the sewage treatment plant, which is, well, the main sewage treatment plant also of the city of Groningen. And then the second advantage is not that you only get industry water, but also that you remove quite some medicine pollution from the Ames channel. Otherwise, the effluent would go to the Ames channel and all the medicine go back to the sea. But in this case, if you make process water, you also remove the medicine, so less medicine ends up in the sea. And the last step is a multi-client approach in the industrial sites. So some companies need very clear water, and other companies, well, they can handle a bit more dirty water or with more salts in it. So the idea is to look if you can connect some companies. That a company that needs very pure water is first, and then gives the water to the second company, and then to the third company. And also the aim is to recycle it inside the industrial site and make a storage underground. Maybe also for seasonal fluctuations, like in some dry months that you have a reserve there in the industrial site and don't need drinking water. And then, this is still in progress. So this is for the future when the first two steps are being made. And then the objective of the second part, where we are part of, is the objective of REgain, to find sustainable, biological, and profitable techniques for the removal of medicine residues and to produce industrial process water. And in this project, 3 different pilots are tested, and they selected the BODAC, Capillary nanofiltration, and Wetlands. And they did this because they were looking at methods that are both biological and sustainable. Well, it's not for all 3 of them. But the BODAC has bacteria inside and activated carbon. And the wetland, of course, is a natural method. And they included capillary nanofiltration because it is a method which can produce very pure water, remove all the medicine, and it still uses only a low amount of chemicals. So that's why they still include this. Then, of course, we need to compare the techniques. For this, we use the STOA guidelines. STOA is the Dutch Research Institute. And so I made a list of 11 medicine residues, which all companies or water institutes in the Netherlands can use. And then So if they screen for these medicines, you can compare all the different techniques and all the different water institutes in the Netherlands. So which technique is best to remove all the medicine? Here's a list of the 11. And they include like antibiotics, painkillers, beta blockers, and they selected them based on the chemical structure. So they looked for medicine like this, a group of medicine would look more equal chemically, and then they selected one out of that group, and yeah, to have a large variety also in chemical structure. And the aim is to remove 7 out of the 11 of these substances for more than 70%. Then it's supposed to be a decent technique. And yeah, of course, you want to aim for 100%. And also in the future, there will be guidelines from the European Union. The European Committee is busy with a guideline for sewage treatment plants. And yeah, then, well, now we are looking mainly for how to remove it from process water, but in the future, also sewage treatment plants need to remove medicine from the water. And here is a picture which shows that it's also necessary, because here are the 11 and some more medicines. And it was tested for the sewage treatment plant in GArmerwolde and also for one other one in the Netherlands. And both are measured for multiple years. And you can see that most of these medicines are indeed present in water. Then I will go on with the next part of the presentation, the regain pilots. But first we could have a small break if you want to, or you can ask some questions. Yeah, maybe.
So your normal water treatment plants, they're unable to take medicine out of water?
Yes, some medicine are easily degraded by bacteria or something, so it's already happening in the sewer system and in the wastewater treatment plant, like paracetamol, it's easily degraded. But other medicine are pretty inert, which is also, some of them are made for that because you don't want your body to degrade it like within an hour. So some of them are quite inert, and they go through your body, but also through the whole sewer system. And yeah, they go to the effluent. They're still in it. Yeah. So some go out, some don't.
If you know what the health effects drinking a lot of medicine?
Yes, for some of them there is. That's also it's tested for most medicine, like what is the level that you will have an effect, yes or no. And also there's this payback value that's more towards the environment, like the level that you assume that there is no effect on the ecosystem. So yes, we see that some, I don't have a slide about it, but it's known that in some rivers, the amount of, for instance, hormones or other medicine is that high that fishes start to change their gender. And another drawback is if you have for instance, medicine that treat fear, if the level in the river is high enough, then some small fishes are not scared anymore, or other small animals, and they are more freely moving around, and then they're easily eaten by other fish. So predation goes up than the small creatures. So yeah, they can see it in, I think, at least in the south and in the river. More questions here? And online, are there questions?
Questions online or other participants online? No.
No. Okay. Then what shall we do? We can have a small break if you want to get some drink, something to drink, or we can go on.
I'm fine, honestly. But,
Sebastian, what shall we do? Shall I continue with the second part?
If the students on site are all right, then let's continue with the second part too.
Yeah. Yeah, the students on site are all right to go
Right.
on.
So then let's continue.
Then part two, about the three pilots that we are working on. So this is also partially the project of Tom and Joost. So you will maybe recognize something from their presentation. So what we see here is the sewage treatment plant in GArmerwolde, close to the city of Groningen. I think the city of Groningen has about 200,000 people. And the sewage treatment plant, I think it's designed for 250 or 300,000 because there's also some industry. Well, you can see it here. It is a two-step system, as they say. First part is aeration to oxidize most organic compounds. And I think that's happening in the yellow part. Then there is a low load system, which is mainly designed for nitrification. And then there are 6 secondary settling tanks, which discharge the effluent in the ditch. So the settling tanks are the blue ones, and is discharging in the effluent ditch here around it. And then here further down is going to the Ames channel. Well, we will take for our pilot some water from the effluent ditch, so it's already purified by the wastewater treatment plant. So the amount of nutrients, organic material, but also nitrogen and phosphorus are significantly reduced. But there might be some micropollutants left. So we pump it here to our the pilot, which is a bit further back. And it looks like this. Well, not anymore. Now it's filled, but this was 1 year ago. So we get the effluent from the wastewater treatment plant. It's split up here. Part is going directly to the wetlands, and part is first going, first to a drum filter to remove still some organic material which was in this effluent ditch, or maybe because there are also trees growing, some leaves are falling in, or there's some sand, and that might damage the BODAC and the capillary nanofiltration. So we remove all solid particles. Then here we see the drum filter. So it's mainly what I said, to remove particles that are still present. When this is the membrane. When it's full, it starts to backwash and wash the membrane with these nozzles to clear the filter again. And in the project of one of our interns, Frank, he tested if there is a significant difference also for the 2 techniques after it, the capillary nanofiltration and the BODAC, if we would put a filter of 15 micrometer there or a filter of 30 micrometer, the pore size. And then here, there's a buffer tank of the water. And this one is operational since November 2023. Then we go on to the first technique. So the water is purified by the drum filter. Then it's going to the capillary nanofiltration. This one was selected since it's an advanced filtration technique, but it still uses a limited amount of chemicals. So it's might be a more sustainable technique. And on other locations, it showed good results, especially for the removal of micropollutants. And this is how it looks. So we have a setup of different capillary nanofiltration units. And inside there is a filter, and this is an overview of the different kinds of filters that are available. So you could have microfiltration, ultrafiltration, nanofiltration, or RO filtration, depending on the size. In this case, we use a nanofiltration with pore sizes of 10 nanometer to 1 nanometer. And here you can see what these type of filters might reject. So the nanofiltration will keep suspended solids, bacteria, algae, viruses, will keep it out, and it can also filter some multivalent ions, for instance, phosphate, which is 3 charges, but the monovalent ions in water go. The unit that we are using in GArmerwolde is from the Dutch company nanofiltration. It looks like this. Inside one of the modules, you have thousands of little membranes that are like straws. This is one of the straws, the cross section. It's a hollow fiber filter, and then in the inside, it has layers. So it's not just a nano filtration unit, but it's also layer by layer. So positive and negative layers are alternating, and that keeps even more chemicals out than you would only predict on the pore size. And then, well, it's going in as a feed stream through the straws. The retentate is going that way, and the permeate, well, the water and the clean water is like pressed out of the straws, and it's going here. Here you can see a bit how it looks with the alternating layers. So the nanofiltration is also coated with a charge, which is keeping like multivalent ions like aluminium and iron inside, and also bigger organic micropollutants, and the water and the small ions permeate over. Well, this is a small flow scheme of how it works. The feed goes in, and then it's like recirculating all the time in the system, and it's pressurized, so clean water goes out, and then more feed comes in, but the concentrate is staying inside. And then after some time, when the concentrate, the pressure is building up because concentration goes higher and higher, it's cleaned. So then with air, it's flushed, the concentrate goes out, and then it's starting over again. And once in a while, there's also chemical cleaning, which is here on the slide. I will come back to it. This is how it looks in Groningen, GArmerwolde. It's this is the unit that we have in the cabin. So this is very familiar to some of our interns. This one is also operational since November 2023. And one of our interns is testing the difference between 400 and 800 Dalton filter, and Dalton stands for gram per mole. So the pore size and which kind of molecules it can retain. It started with a recovery from 65%, which means that from the effluent water, 65% becomes the clean water, the permeate, and only 35% is concentrate, and they're building up to that. From that, I think now they are at 85 or 90%, so it's really increasing. Well, we have this this cleaning. So when the concentrate goes out, and sometimes they use forward flush and sometimes backward flush, and then when it's really starting to be polluted, they do a chemical cleaning with both basic step and an acidic step to remove all and degrade the organic pollution that's inside. Here are some general results from capillary nanofiltration. So what we would expect is that large micropollutants, which has a size above the pore size, will be rejected or will end up in the concentrate. For instance, this antibiotic with size of 748 gram per mole. you will expect that it's definitely rejected by 400 Dalton filter, because, well, it's almost twice as big. But it's in this case also rejected by the 800 Dalton filter. It's like on the limit, but it also has a positive charge. So it's yeah, almost the size of the pores, and it's charged. So it's nice one. This will be filtered out. And then that holds for more molecules, which have a molecular weight just below the pore size, but are charged, then they are rejected. And also some smaller compounds with which are diatrivalent ions, like phosphate and sulfate. And passing through are non-valent ions and some much smaller molecules, or medicine or micropollutants, like for instance, well, the sugar glucose, which is 108 per mole. Then the second technique, the BODAC, is a biological oxygen dosed activated carbon system. And it's a filtering method which both uses the activity of activated carbon, which can capture organic pollutants, but also bacteria can grow inside of this activated carbon and consume some of the pollutants which are captured by the filter. And to help, or yeah, the bacteria to degrade all the organic material, is aerated. So they have a higher oxygen level inside. And there's one location in the Netherlands, in the province of Drenthe, in Emmen, that has this method in full scale, and it showed good results for the removal of pharmaceuticals also on the long term. And here is this plant in Emmen. It's from Neuwater, and it's an ultra pure water factory. This is the sewage treatment plant part, and then here you have the ultra pure water factory. So the ultra pure water factory gets effluent from the sewage treatment plant. Then there's an ultrafiltration step to get some of the larger particles out to prevent clogging of the BODAC. Then there's the BODAC cleaning. And then after that, they continue with 2 more steps of RO filtration, because they are a factory to produce ultra pure water to produce steam. And in this case, for the mining company of the Netherlands, the NAM. But for our process water, we don't need super ultra pure, so we will stop after the. And how does it look inside? This is the BODAC pilot in GArmerwolde, where one of our interns, Joost, is working on. It's about 4 meters high and it's filled with activated carbon. And then on the activated carbon granules, there's an organic layer accumulating of some metals or minerals, calcium, iron, manganese. There's also a microbial community growing on it. And this community produces a biofilm, which is built up of APS. Here are some results from factory in Emmen. This is published by people from Wetlands. And they show that the BODAC itself can remove part of the organic material that's left, like 10 to 45%. It performs full nitrification. Iron is removed for 30 to 70%, and manganese almost fully for 99%. And these 4 medicine residues are removed for more than 70%. And this BODAC treatment plant in Emmen is already operational for 10 years without exchanging the activated carbon. So it's really a nice system that can recover itself. Well, and then one of the pilots from Emmen was moved to GArmerwolde. We had some research questions like, is the material still active when you take it out of M and move it here, because it's the bacteria inside are aerobic, and during the transport there was not always aeration. Does it also work well on the wastewater effluent from GArmerwolde? Of course, both with our sewage treatment plants in the Netherlands, so the water is comparable but slightly different. And how does it compare to the other pilots? Then we have here the third pilot that we are testing, Wetlands. They are constructed wetlands, so not a natural big one, but in pilot system with halophyte filter on top. And this is one of the most environmental friendly methods to purify water. Just to use nature's capacity to clean the environment. How does it work? The system that we have is a filter bed filled with clay granules, and top some weeds or halophyte plants are growing. Wastewater is coming in from the top, going through it vertically, and then clean water goes out here. I will have some more pictures of the actual pilot later. It's produced by a Dutch company, Wetlands, and they give a nice overview of the different wetlands on their website. So there's a possibility for a vertical system, horizontal system. It can be aerated, and or just a regular flow field. And then all of them have different characteristics for the amount of pollution that you can put on it and can handle, the degree of purification that you will get, and the capacity, the amount of flow that you can run through it. In this case, we have a vertical system, but it's also aerated from below with air. So it's a combination of those two. It can be heavily, it can deal with heavily polluted water. Degree of purification is very good, but the amount of flow running through it needs to be low. This is how it looks in GArmerwolde when it was built up. We have 3 different setups after each other that we can compare. It's here filled with the clay beads. And then there are some tubes here for sampling, and they are all at different heights, so we can take samples with different heights in the filter bed. And then, well, this was in the beginning, so the small halophyte plants are needed. And here you can see that there are some white dots, spots, and that's the bubbles coming through the whole filter bed. They are filled with 3 different types of leca granules. One with smaller ones from 4 to 10 millimeter granules. One with slightly bigger ones, 10 to 16 millimeter. And then a third one, which has the same granules, but then there's a small layer in between of 6 centimeters of activated carbon. And we did this to increase to help the system to start up. Because if there are only clay granules, it's not really purifying micropollutants, but if you have a layer of activated carbon, it will already from the start filter some micropollutants out. And then after some time, the whole system needs to will do this. So if bacteria and plants are growing, they will take over. So then it's less depending on the activated carbon. What I said, it's a vertical flow system. It's continuously aerated to keep the oxygen level at about 7 milligrams per liter. And the whole system has a hydraulic retention time of about 12 hours. And we know that it's fully converting ammonia into nitrate. This is how it looks now. So the plants grew a bit bigger, but still it needs some time to become a full grown wetland. And research questions here are like, is it really a benefit to add this activated carbon layer? Which setup works best out of the three, and how does it compare to the other pilots, the BODAC and the capillary nanofiltration? And well, these were the three pilots that we are testing, and what would we like to gain from the whole REgain project? At the end, the whole project will take about 2 years, I think, or 3 years. So the pilots will stop in 1.5 years now. At the end, we like to have a clear overview of the three techniques and well, be able to give an advice like which technology is most suitable to treat the wastewater treatment effluent of GArmerwolde to become processed water and to remove the medicine residues. We would like to have full-scale design parameters at the end, make a business case. And the nice benefit of this whole project is that we also include students and interns in the whole process. So there's an educational part. Yeah, REgain is also in collaboration between the industry, the government, and education universities. And at the end, well, it will also knowledge will be disseminated to the harbors, to the industrial sites, and the drinking water companies. Here are the partners again that I showed at the beginning. And here are some other parties that are connected to this project. Since, well, we cannot do it alone, so we do it with all these parties together, like our provinces, government, some universities, and of course the drinking water companies. Okay, that's my presentation. Thank you for listening. Do you have questions? Yeah.
So what is the point of aeration with the wetlands?
Yeah, to also increase the amount of oxidation that's happening in the filter bed. If you wouldn't do it, I think the whole bed or part of it will be mainly anaerobic, and then you get a certain type of bacterial species. And if you aerate it, you can also get different types of species. And usually the ones that are aerated are faster oxidizing. So I assume the whole process speeds up when you have aerated filter bed. Other questions? Yes, of course.
So with the activated carbon, when it gets filled up, does that get rinsed out or you switch it? Like so have a backwash or something?
In the wetland or in the?
No, like a tall stack.
The whole in the BODAC system. Yes, we backwash it. So at some point the bacteria, of course, we are feeding it all the time with the effluent, and there are nutrients inside, so the bacteria can grow slowly. So at a certain point you will have a buildup of bacteria and maybe also organic material from the sewage treatment plant. So if the pressure builds up, we will do a backwash to wash out all the bacteria that are too much. Any other questions? And Sebastian, do you have questions? Or are there questions?
No, no question from my side. Thank you.
And Bonita left, right?
Yes.
Yeah. Okay. Then I think this is all for now from my side.
Thank you very much for the nice lecture.
Yes, you're welcome. Thanks for hosting.